Welcome back. In this video, we're going to talk about converting regular expressions into non-deterministic finite automata. Before we get started, I want to give you an overview of the plan for the next few videos. We have a lexical specification that we want to implement, and the first step is for someone to write that down as a set of regular expressions. Now, that by itself, of course, is not implementation. That's just a specification. So we have to translate that into a program that can actually do lexical analysis. And this actually happens in several steps. The first part is to translate those regular expressions into non-deterministic finite automata that recognize the same, exactly the same thing. And then those non-deterministic automata are translated into deterministic automata. And finally, those deterministic automata are implemented as a set of lookup tables and a little bit of code for traversing those tables. So in previous videos, we've talked about this piece, and we've also defined these pieces. And so now we're ready to put the whole thing together. And in this particular video, we're going to focus on this component right here, the translation of regular expressions to non-deterministic finite automata. So the plan is that for each kind of regular expression, we're going to define an equivalent non-deterministic automaton, an automaton that accepts exactly the same language as the language of the regular expression. And here's a little bit of notation that we're going to use. We'll define these automaton for regular expressions, and usually what we're going to be doing is needing to modify their start states and their final states. So we'll just indicate the start state with the arrow and the final state with a double circle, and we won't worry too much about the overall structure of the machine as long as we have a handle on the start state and the final state. And I should say that in the machines we'll build here, there will only be one final state. Okay, so let's begin. So for the Epsilon regular expression, what's a machine that accepts that? Well, this is a very simple machine. We just have a start state and a final state and an epsilon transition between them. So this machine accepts exactly the empty string. Similarly, for a single character A, we can define a one transition, two state machine that accepts that one character. So from the start state, we can move to the final state if and only if we read that particular character. Okay, so those are our two simple regular expressions, and now we have to do the compound regular expressions. And these are a little more involved. So let's talk about concatenation first. And so because we're going to build these machines up from smaller regular expressions to larger ones, we can assume that we've already converted A and B separately into machines. And so I have a machine for A, and I have a machine for B, and now all I have to do is say how I'm going to paste together these two machines to form a machine, a compound machine that recognizes the same language as A concatenated with B. And here's the construction. The start state for the compound machine will be the start state for A, so we just keep that start state for A the same. And then we modify the final state of A. So we make the final state of A no longer a final state, and I've done that here by removing the double circle on the final state of A, and we add an epsilon transition to the start state of B. Now, if you think about it, that does exactly the right thing. What that says is that first we recognize some portion of the input that belongs to the language of A, and when we get to what would have been the final state of A, we can jump to the start state of B without consuming any input, and then try to read the rest of the string as part of the language, as a string in the language of B. And for union, we have a similar way of pasting together the machines, although the structure is somewhat different. So here we add a new start state for the compound machine, and what does A plus B means? It means either the input is in the language of A or it's in the language of B. And epsilon transitions are really good for capturing this because we just make a decision right from the start state, is this string going to be in the language of A or is it going to be in the language of B? So we make a non-deterministic choice, and then we read the string as using the automaton that we chose. And if we get to the final state, either of those machines, we can make an epsilon transition to the new final state for the compound machine. Now remember what the notion is of acceptance for non-deterministic automata. They make these guesses, but if there's any guess that works, then we say that it's in the language of the machine. So if in fact the string is in the union of A or B, then either choosing A or choosing B will work, and so the machine will accept the string. And finally, the most complicated case for iteration A star, we have the following construction. So here's the machine for A embedded in here. We've added a new start state and a new final state. And now let's talk about how this works. So one possibility is, remember that epsilon is always in the language of A star. And so we have this transition here. We can go straight from the start state to the final state and accept the empty string. And so that just guarantees that the empty string is in the language. Otherwise, what do we do? Otherwise, we can make a transition, an epsilon transition to the start state of A, and then we can, from the final state of A, if we reach it, we can go back to the start state of the whole machine. And we can do this as many times as we like. Okay, so there's the iteration of A. It's around this loop right here. Right, and when we reach the final state of A, we could also decide to just make a transition to the final state of the machine. We conclude that that's the last time. And so this machine recognizes 0 or more strings in the language of A. So now let's do an example. So here's a regular expression, and we want to build a equivalent non-deterministic machine that recognizes the same language. And we're going to follow our construction, which works by induction on the structure of the regular expression, starting with the simple regular expressions and building up to the compound ones. So what do we have here? So we have a machine for accepting 1. Okay, so we need a machine that accepts 1. If you recall, it had 2 states, and it just it made a transition between the two on the number 1. Similarly, a machine for accepting 0. Okay, and now we need to put them together in a machine that accepts either 1 or 0. And the way we did that was we made a choice from a start state for the compound machine. We can either move to the machine for accepting 1 or the machine for accepting 0. And then we have, at the end, also epsilon moves back to the final state of the compound machine. Okay? And now we need to iterate this, so we need to be able to accept 0 or more of 1s or 0s. And so we're going to take this entire block here and paste it into the pattern that we had for iteration. So how do we do that? Well, we have a new start state and a new final state. Okay, and there's an epsilon move from the start state to the new final state to guarantee that we accept the empty string. And then we can just iterate this inner machine as many times as we like. We can make an epsilon move to the start state. We can execute the machine once. And if we decide we want to do it again, well, we can do that. Okay, go back around for another time. Or from the final state, we can decide that we've seen enough, and we can just move to the final state of the compound machine. So this machine then accepts the language 1 plus 0 star. And now we have a little bit more to do. We have to accept, we need another machine that accepts just 1. So we build another machine that accepts the digit 1. And now we need to compose the two of these things, to concatenate them. And that was very simple. We just have an epsilon move from the final state of the first machine to the start state of the second machine. And then these are all the states of the final machine. And we just need to now label our final state, though the state that we're actually going to use in the end is the final state of the entire machine, which would be that one, and the start state, which is this state over here. And that's the entire construction for the non-deterministic automaton, or a non-deterministic automaton that recognizes this language.